Alright, I'll just get into this. I am actually in a differential equations course right now, and I'm preparing for my final exam, which is tomorrow. So I just thought I would review kind of everything we covered um, in a relatively short, fast kind of way, just to kind of get the overview. And it's much more interesting to me to review while making a video. And I thought maybe some people would be interested to see what is covered in this class, like in general, kind of touching on at least most of the main themes. There's a couple things I'm going to skip because they were really not interesting to me, but for the most part, I'll touch on all of the big ideas and work through some examples. I'll probably have some of my work wrong in what I do, but the basic idea of what I'm doing will be correct. I just didn't bother to work out everything ahead of time, and uh, I don't want to use the exact same examples that were given in class because I don't know if that's frowned upon. So, um, yeah, so what? Oh, come on. There we go. Okay, so uh, the main ideas that are covered. So I'll just kind of briefly go over the big ideas first and then step it back a little bit and start to explain in a little more detail what a differential equation is. I'm thinking that most people who would find this interesting or useful are people who haven't taken the class yet and who just don't know what a differential equation is. You'll need to have a decent idea of what derivative and an integral is, because a differential equation is just an equation that doesn't only have variables, say x, y, t. It also has as a variable a derivative or a second derivative or third derivative, some order of a derivative in the equation as part of the equation. The basic idea is that's what a differential equation is. Things that are covered in the class would be things like how to classify them. So there's first order, second order, uh, linear, nonlinear, homogeneous, non-homogeneous, separable. So then you get into different ways of solving the different types, which is why they cover the different types, because you can't use the same method for every single differential equation, and many differential equations don't have a method that you can use that would give you the exact solution. You would have to use an approximation. But so some methods that they cover are the method used for if there's separable, constant coefficients, undetermined coefficients, Laplace transform, and then other things that are covered in the class would include some types of examples, practical examples, such as a spring and mass system. I mean, they're not really that practical, but they're kind of, it gets away from just numbers and into applying it to a real situation. Mixing problems, population growth. Then the thing that I was not interested in, so I'm pretty much going to skip it mostly, are different methods of determining whether you can have a unique solution or where your unique, for what domain your solution could be unique. The Wronskian, which fits in with that. Euler's method, which is a method for approximating, which is familiar to in Calc 2. There's methods for approximating integrals, which the basic idea of an integral, this isn't really probably the best way to start for like a formal definition, but probably the easiest way to grasp the idea quickly, to get the basic idea of it, would be an integral would be the area under a curve. So if you have a graph that has some kind of a curve on it, any kind of shape, the area between the curve and the horizontal axis would be what the integral gives you if you give it bounds on each side. So that's the integral, and there's lots of fancy math used to solve the integral. But if you have an integral where you can't use fancy math techniques to find an exact solution, or perhaps you just don't want to for whatever reason, you can also use methods to approximate, and you can actually approximate it out really far so that for practical purposes it may be as good as the real answer, even though it's not exact. So the same idea applies with differential equations. So differential equations, and I'll get into like actually using the images here, doodle pads. So the first thing that's covered, and probably the best place to start, would be direction fields. I don't know how far over my tablet goes here. I think that's the limit. I've seen different names for these. I don't actually know which one's the most proper or the best. Maybe some kind of fields. I think direction fields, slope fields. I don't know if there's a difference between them. This is the only context in which I'm familiar with fields, so I don't know about the other when which term is better. But the basic idea is, so normally if you have a graph, and say those are your axes, so your graph might look like this if it's a sine wave, or you may have a graph that looks like this if it's a straight line. So what a direction field is, if these are your axes, it would be a bunch of little arrows, and it's really hard to draw these, so usually it's done with a computer or some type of program designed for creating these. But so all of these are dots in space that show the direction of the slope at that space. Yeah, that's about as good as I can do with those. We'll go ahead and graph one of them, I guess, for an example. So you have different dots all over. So it's kind of the basic idea. It's really hard to draw them. So clear this back out. So direction fields, and we'll go ahead and graph one. I'm just going to pick a couple of functions that, for illustrative purposes, that keep bringing up over and over. So this is dy over dx equals xy. So this is a differential equation. You'll notice that it is the derivative of y with respect to x equals xy. And this would also be, you may also see it written this way, y prime equals xy. That stands for the same thing. It's just in this notation you don't know what the independent variable is that relates to y. When you just say y prime, you don't necessarily know what the dependent variable is. When you say dy over dx, you know that y is the independent variable and x is the dependent. Y is the dependent variable and x is the independent variable. So yeah, this form here is nice. I'm all the way on the edge of the thing. So this form here is nice for certain methods of solving differential equations. So the first one, and this is probably where places usually start, is the idea of separable differential equations. First, let's actually graph this. So we have, if this, so let's say that we had some graph, right? A different equation. Let's say this was y equals x. And you wanted to graph it like your very early days, you're first learning how to graph functions. You would say, you'd pick x over here as your independent variable, you'd pick y over here as your dependent variable, you would pick some values for x, say -2, -1, 0, 1, 2. You would plug in from the independent variable x into the equation and see what y value you get out. Since I did x equals y, they're all going to be the same. -2, -1, 0, 1, 2, and then you would graph it by making your points, you'll just have to imagine the tick marks on here. So we are at -2, -2, then you go to -1, -1, then you go to 0, 0, then 1, 1, then 2, 2. We're in there. Then you would connect all of them to make a graph. So that's traditional graphing. If you were to graph a differential equation, so dy over dx equals xy, you would say, you'd have a column, sorry, you would need two columns, x, y, and then you would need the output column, which is y prime, which is the same as dy over dx, or derivative of y, or derivative of y with respect to x. This all means the same thing. So, and in this case, you're going to have to pick variables for both x and y and see what final y output you get. So let's say if we were to pick, I'm just going to do, I'll do 5 points again. So let's keep x at -2, -1, 0, 1, 2. Then for y, let's use, I don't want to use all the same ones. I'm not sure. Let's do this. How about 1, 2, 5, -1, -2. I don't know if that was, maybe I would have been better to go in order. I've not graphed a whole lot of these by hand, so I'm not sure if that was the best for illustrative purposes, but I'm not going to make this video more than once. So now if you plug back in our differential equation, which I'll just rewrite it right here, derivative of y equals xy, x times y. So a -2 times 1 is -2. -1, 2 is -2. 0 times 5 is 0. -1, 1 times -1 is -1. 2 times -2 is -4. So there's some derivative of y. And if you know from calculus 1 what a derivative means, I kind of said briefly what an integral means, but the basic concept, again, there may be better ways and there are other ways to define the basic idea of a derivative, but what I think is probably the easiest to grasp and is the most relevant for this graph right here, a derivative represents the tangent line to a slope. So if you have some graph that looks something like this, the derivative at this point would be the line tangent to that point. So it's this. That's the derivative. And for some reason I can't think of the way to put it into words correctly, but as you can see, it's just a straight line with a certain slope. The derivative for this point, which is the tangent line, which means the line that touches that point and only that point is equidistant from all other points nearby. So there's another tangent line. Those happen to look parallel. Let's say this point right here, the tangent line would probably be, pretend that's a straight line. For some reason I can't draw vertical straight lines. So I did pretty good horizontally. Yeah, I can't. Hard because it's on a tablet. All right, just have to use your imagination that that's a tangent line. So anyway, basically tangent, the derivative represents the slope of the tangent line. So over here we have a bunch of slopes in this column. And these are still our traditional points. I'm imagining this is the y-axis, and this is positive, and this is the x-axis, and this is negative, as what is pretty standard in the beginning stages. And I guess just you can say standard in general, it's standard. So we go x -2, y1. So it would be this point, but we're not graphing a point, we're graphing a slope. The slope is -2. So 0, it's down. I think how big. Okay, so if this is 1, I think it should be something like this, except it should be really tiny. And you don't really need the arrows, but so there's a line, there's a little tick mark there. Now we go our next point, or our next plot, I guess, -1. So it's going to be here, +2, roughly here, and we have a same slope, -2. Then if we go with 0, 5, but we have slope of 0, so that's a slope of 0. Then if we go with 1, -1, about here, and we have a slope of -1, which should look like that. And if we go with 2, -2, we have a slope of -4, which is going to be pretty steep. So like that. So anyway, had I picked better points, it might be easier to visualize. So for example, had I picked a whole bunch of points in this column here, then you could see patterns as you move up this column, patterns in how the slope changes. And the same throughout, and the same for the picking in points that line up in horizontal rows, then you can also see patterns emerge. And basically what happens then when you solve a differential equation, you have all of these tick marks, which now I'm just going to start to make them up because it's going to take too long to do all of them properly for this particular graph. But let's say up here we have this keeps going like that. Let's say as we move up this row, these slopes start to change and eventually go like that. Let's say right here, the slopes are just a little bit milder than their neighbor and maybe go down a little faster. And let's say right here, they also go down even faster until maybe down here they reach a straight down line. Okay, so this is just completely a made up representation of what a slope field could look like. I'm not even sure if this is technically possible, but the idea then is what the solution for this looks like is going to be an equation, meaning it's going to, the solution will be some graph, which here I have the dependent variable y, because I'm taking the derivative of y, you take the derivative of the dependent variable, and x is the independent variable, so my solution will be some equation in the form of y of x equals something, some text right here, and it will have some kind of a constant, an unknown constant in there, meaning it's intended to be a constant, not a variable, so it doesn't change with respect to whatever the independent variable is. So it won't change with respect to x, or if this was time, which is a little more intuitive, it wouldn't change with respect to time, but at the same time you don't know what it is yet, so it still is just listed as some letter. They usually, excuse me, as you see later on, they're going to use C1 and C2 quite a bit for those. So, or I guess just C. If you only have one, it would just be C. And you'll recognize, if you've done calculus too, from taking integrals and doing integration and solving integrals, you have the integral will be some kind of text with a plus c at the end. So some numbers or whatever, some kind of function plus c, because that's a constant. It's not a variable, it is a constant, but it's a constant that you don't know what it is yet because you don't have enough information. So typically in later problems, more information will be given besides what I have written right here for our initial differential equation. You'll have more information given to figure out what the constants are. But for now, I didn't give that. So basically the idea is, the reason that I said all that is because it's necessary to understand what this represents. So the final answer, the solution to this differential equation, is a y of x function. But it's not a particular y of x function, it is a family of y of x functions, just like when you take the, I feel like I don't quite understand the difference between the terms antiderivative and integral, but I'm just going to use the word integral. So when you take the integral of an integral, when you solve an integral, what you get is a some, I don't want to say this, I don't think I want to say function. You get your solution again with a constant because you're actually finding a family of solutions. It's not just a solution, it's a family. And unless you're given some initial conditions, then you can't find the specific solution. You can only find the family of solutions. So it's the same with differential equations. You're finding a family of solutions, and if you're given initial conditions, you can find the specific. And if hopefully I put enough dots on here. I don't want to keep drawing dots forever, or little slashes forever. Let me just draw some more so you can kind of get the idea. So you can see as you look at these, they should be evenly spaced in columns and rows, but it's going to take too long to do that. So basically though, if you imagine these were evenly spaced in columns and rows, then what you have is you pick your initial conditions will allow you to start at a starting point. So let's say I was to start here. Then, and I'll use a different color. The orange will show up good. So let's say you were to start here. Now, your initial conditions would then tell you that basically you're following the paths of the slopes. So you would kind of follow wherever the slopes seem to lead, and that would like trace out your graph, which here you can't tell because I didn't draw enough, but let's just say it went up like that. So that could be one path, but if your initial conditions started over here, then the solution could be a line that looks maybe like this. I don't know where they go here because I didn't draw them in, but just you would really be able to see it better if it was a better graph. So these are two potential solutions that could be solutions depending on what your initial conditions were. Now, back to where I was a little while ago with the idea of we have this differential equation dy over dx equals x times y. And if you want to solve this, aside from, randomly graphing a bunch of plots and then kind of doing some guesswork and some rough tracing, if you want to solve this in a little more precise way, one way you can do is this dy over dx, you can't separate the d from the y and you can't separate the d from the x, but you can separate the dy from the dx. So you multiply both sides of this equation by dx. This is called separable. It's called a separable differential equation. So this is solving it by separating. I'm sure there's a better way to say that, but that's what you're doing. So dy equals, because when you multiply this side times dx, both cancel. Those cancel. Then x times y times dx. So now you could integrate this side if you could get the y to the other side. So you're going to multiply both sides times 1 over y. So these cancel. So this side has 1 over y. So 1 over y dy equals x dx. Now what you can do is integrate both sides. And integral, sorry for the sloppiness, writing on a tablet's weird. So the integral of 1 over y, write it down here, should be the natural log of the absolute value of y plus c equals x squared over 2 plus c. And then usually though they don't use two different c's, so technically this should be like, we'll call this plus a because it's just a constant. We'll call this plus b, it's a different constant. If you subtract a from here, you get b minus a, which is just a different constant. And because you don't even have your initial conditions yet, later on when you throw in your initial conditions and solve for your constant, when you combine two unknown constants, you'll end up with the same result. if you combine them now into a new constant, or if you were to leave them separated and wait until after you threw in all your initial conditions. Let me move this over here. So right now we have natural log of the absolute value of y equals x squared over 2 plus c, because I combined the a and the b into a c, or technically I combined the b and the negative a, because it would be negative moving it to this side. Now to solve this, then the goal is to get a function for y by itself, because y is the dependent variable. So we want it to be y of x equals something something. So we can say e is the natural log of the absolute value of y, and actually these absolute value signs can be dropped because just they always end up being able to be dropped for types of equations. We raise this side to e. I'm going to separate this out, 1/2 x squared plus c. Then we take e, how to say this? I'm not all that great with logarithms. For whatever reason, this simplifies to be y. E to the natural log of something can just become that something. Yeah, I'm not going to sit there and try to explain. That'll take too long. So y equals e to the 1/2 x squared. Then you can, this plus c, you can change this into e to the 1/2 x squared times e to the c. Now you'll notice the idea of constants applies again. So this could be e to the c. E is a constant. It's a funky number, but it's still a constant. C is a constant, so we can just change these into a new constant. You could call that d, and that would probably be a little more proper, but usually all of these steps are skipped and everybody just calls it c, so I'm going to call it c. So y, again, this is y of x, y and y of x, that means the same thing, equals c e to the 1/2 x squared. And this is the general solution to our differential equation. And if you had some initial starting conditions, an initial value for x and an initial value for y, then you could plug those in and solve for whatever c is. And when you solve for that c, that's basically going to tell you which specific graph you mean on this slope field. But if you don't have that initial value for c, your equation can represent any graph on the slope field. And once again, this does not accurately represent the actual slope field for the equation, because I didn't prepare ahead of time and it would take way too long to sketch it all out. So there's the first part of like what you would learn. And I'm kind of going to save this because I'm going to keep using this equation later. So let's actually do this. Oh, I want to do this. Let me rewrite it. I wasn't on any space. All right, where'd my mouse go? Ugh. There it is. Okay, so let me delete this. Let me get back to this color. And for these, we'll use red. So this will be my little corner of stuff to save. All right, so we have our differential equation that we started with was derivative of y. Oh, hold on. I'm off the thing anyway. And now it changed to white. I don't know why it changed to white. All right, so derivative of y equals x times y And then the solution for that is y equals c e 1/2 x squared. Okay, so we'll kind of save that for right now. And the rest of this I want to delete. Fill it back in. Okay. All right, so the next thing, so direction fields, another thing that would be interesting to talk about then, so that's your first taste of solving a differential equation, how to visualize graphically what they mean, and then the simplest first way to learn to solve them. The next thing would be learning some kind of practical application. And so the application, there's actually a whole bunch of different applications that were presented early in the book. Just to present one of them was the concept of drag. And so, so a little bit of physics. See how much do we actually need to solve this problem? So let's say you have some object and it's falling in this downward direction towards the Earth. It happens to be relatively close to the Earth. Here's the shadow. And as you can see, it's not very aerodynamic, so we're going to consider air drag. We're going to very loosely consider air drag because when they present it in a math class, they don't go over all the details because it's really just to illustrate the usefulness of the math as opposed to explain all the details of physics. And so far in physics, I have not really covered how drag fits in. It's actually in the sections we went over, we just skipped over it. So basically, I'm going to do my best to explain this properly. But the basic idea here, what do we want to start with? So if we were to try to add up forces, we have a downward force. That's actually pretty hard to see. Let me pick a different color. What did I use before? Was it this one? That's not so bad. That's not so great either though. Let's try pink. That's a little bit better. Okay, so we have a downward force, which is the force of gravity. We don't have any forces working horizontally, and we have an upward force, which technically should be a smaller arrow because it's going to be a smaller force, and we'll call that force of drag. Oops, be a D. Force of drag. So the force equals mass times acceleration, and the sum of the forces equals mass times acceleration. And here we have some object. It kind of looks like a piece of paper. Let's pretend it's a little heavier, like a steel sheet. And for whatever reason, we're just going to assume that it doesn't rotate as it falls. I guess this would probably could rotate as it falls. We're just going to assume that it just falls straight for whatever reason. Maybe there's actually a pipe running through the middle and it's actually sliding down the pipe, so it's not fully a free fall. Whatever the case, we're going to assume that. And so so force, the sums, let's take, it doesn't really matter so much. Let's take the downward direction to be the positive direction and the upward direction to be the negative direction. So the force of gravity is acting in the positive direction. The force of drag is acting in the negative direction. So we're going to have force of gravity minus force of drag equals the mass times the acceleration. And what we're actually going to try to find here is the acceleration. I didn't mention that yet. And let's see, what else do we need? So the force of gravity is also going to be mass times acceleration, which let's pick a mass for this. Let's say it's 2 kilograms. So maybe it's a hunk of wood. I'm not really familiar with kilograms, but that sounds about right in my head. Maybe a certain thickness piece of wood, certain size could equal 2 kilograms. So we're going to have 2 kilograms times acceleration minus, and then force of drag is often given for these as part of the setup of the problem, and I took really lousy notes for that, so I think that's all I need right there. We'll just leave that as force of drag for right now. I didn't write down the full text that they usually this would be a word problem. Equals mass times acceleration. I'm missing something in there. Okay, the force of drag is supposed to be equal to some constant, which would be based upon the material that you have and I want to say the thickness of the air. I'm sure there's a more technical, better way to say that, but how resistant the air is to the flow of the object and how resistant the object is to flow within the air. So this force of drag is going to be, there'll be minus sign, c times the velocity squared. I think that's it. The acceleration right here, I should have wrote that in, that's g, which is often 9.8 meters per second squared. So we're going to have 2 kilograms for the mass times, and I made it in the positive direction, so it's a positive acceleration, positive 9.8. I'll leave units out because I'm running out of room, meters per second squared, minus c times velocity squared equals 2 kilograms, which again I'm going to leave units out, times acceleration, which is what we're looking for. Now you can divide through by 2 from every term, which is the mass. So you have 9.8 minus this constant, which would be given if you were to actually solve the problem, velocity squared over 2. Either it would be given or you would do a bunch of tests to try to measure and determine what that constant is based on your probably your altitude. I've never really done these kind of problems, but the altitude should probably affect the thickness of the air, and your object would make the big difference, your shape of your object, your material, and that kind of thing. Equals acceleration because the 2's canceled. Okay, and then the only other thing we need, trying to solve for acceleration. Yeah, so we're good to go. So then the thing that you need to know here, which is taught in Calc 1 and 2, acceleration is the derivative of velocity. So a very handy thing that's learning calculation and that's learning Calc 1. If you have some graph and you have the x-axis is time and the y-axis is position, it would probably be either the t, anyway, position versus time. So if you had this graph and you had some, say, like this graph, that represents the change in position. If you were to take the derivative of this, which once again, that represents the tangent line, so some tangent, so the derivative to the graph right here could be this tangent line. Imagine those touch. And this then would represent velocity. The derivative of position will give you velocity. then if you take the derivative of velocity, which should be, yeah, there's no, as I drew this, there's no change. I don't know if I did that accurately. I could know if I were to think about it more, but I mess up when I'm multitasking. So this then could be the acceleration when you take the derivative of the velocity. Okay, and so the reason that's useful is because acceleration equals the derivative of velocity. So now we have 9.8 minus c times v squared over 2 equals the derivative of velocity with respect to time. And now this is a differential equation. And I think that's about as far as I want to go. Yeah, because go back to the order thing, which I mentioned earlier briefly, but didn't talk about it at all. Here, our dependent variable is v, and the highest v value we have, well, no, this wouldn't be this. Okay, so this is first order because the derivative is only a first derivative as opposed to a second, third, or fourth derivative. So this is a first order equation. Then the fact that the v is squared doesn't matter because it's not a derivative of v, it's just v. But then as far as is this linear or nonlinear, this should be nonlinear. I didn't mess that up. I didn't review this because it wasn't important to me. I don't think it's going to be on the final, but this should be nonlinear because the v does matter for that part of it, and it's squared. If there were t's in here and the t's were squared, since they're the independent variable, they don't matter. But the v squared here does matter. Yeah, so if you were to try to rewrite this in the more standard form that you use for solving integrals later in the material, this would be dv over dt minus d over 2v squared equals, no, that's plus. I moved it to the other side of the equation. So it's plus. This stays on the same side it's already on. 9.8, which also tells you that this is non-homogeneous. Because the difference between homogeneous and non-homogeneous is when you write it out in kind of standard form, which basically means you have your dependent variables and your derivatives on the same side of the equation, usually in descending order, and then anything else on the other side of the equation. If the anything else on the other side of the equation is equal to 0, then it is homogeneous. And that matters because it's going to change what you do when you solve it. If it is not 0, then it is non-homogeneous. Okay, so that's enough on that. There's one practical example of when you could use this. I didn't finish, but you could finish if some more. I mean, you could finish now by finding the equation, which I just didn't do, or you could finish even further by finding the c value, the constant, I guess the proportionality constant, if some initial conditions were given, say the velocity at a certain time. No, it should be the, wait, it should be the, yeah, the velocity, no, the acceleration at a certain time. I don't know if you need velocity too. I think you need velocity, the velocity and the acceleration at a certain time. Then you would be able to solve that more fully. So let me erase this and move on to the next topic. Let's get back to purple. The pink was a little hard to see. Okay, so there's one taste of a sample of when they could be used in reality. And the main benefit, as far as I can tell, that, not being an expert, but what I think the main benefit of using differential equations is that it is much easier to get from the real world situation or the story problem to the mathematics through differential equations instead of trying to. Some of the problems seem very strange when you first see them and you think, how could I possibly set up this problem? What setup method could I use to get the math down, the initial math down on paper so that I could actually solve this problem? And once you learn to use differential equations, it creates a very nice bridge between reality or the story problem to the mathematics to find the specific solutions that you're looking for. So that example, I think, illustrated that. What would be next in our little taste of differential equations discussion here? Population modeling. I like the practical applications more, so I have a little more examples of those. And there were all kinds of modeling examples given, and I don't understand them well enough to just make them up on the fly. I did a little better when I was reviewing for this part of the test, but this is from early in the section. So let's say that we have some population and it grows. So yeah, actually I wrote down the wording of the sample problem. So say we have, the only things that I need to fill in are my size. So let's say our initial size of the culture of bacteria is, let's pick really round numbers. Let's say 500 bacteria. Then we have some time, which will be after this certain time, it grows to another size. So let's say the time is 15 minutes. Let's just make it grow stupid fast. Let's say that the new size is, I should write out population, but size is a shorter word. So the new population is 10,000. I think that's fast. Sounds fast to me. So 10,000. So let's say we have this. So the problem may be worded like a bacteria culture starts with a population of 500 and grows at a rate proportional to its size. So what that means is, which this is actually the key to setting up the problem, the rate of change of the population, we'll let capital P stand for population, rate of change with respect to time equals, it is proportional to means there's some proportionality constant. You can give whatever letter you want. I'll write a K here. Proportional to its size. So P would be, again, standing for its size. It stands for the population. So it's proportional to its size. Proportionality constant, whatever represents the thing that it's proportional to here, what would be some function P of t. So these are, P here is a function, this is P of t, this is P of t, this is a constant, this K, this P is a variable that changes with respect to time. After some time, say 15 minutes, there will be 10,000 bacteria, 10,000 little guys. Express population as a function of time. So this is the rate of change of population. You can solve this. This is easy, nice first order, because the highest derivative in it is a first derivative. It is linear because well, I suppose the best way to explain would be if you were to write it out as dp over dt minus kp equals 0. When you write it in this form, the like standard form, there are no, whatever the dependent variable is, which is p in this case, it's never multiplied by itself, multiplied by anything else. You're not taking sign of it. You're not taking it to any power, raising anything to it as a power. Basically, anything out of the very ordinary, very basic math functions, you're not doing any of that. So yes, to either it or to a derivative of it. Multiplying it by a constant is okay, or multiplying it by the independent variable is okay. But multiplying it by itself or a derivative of itself would not be okay, for as far as, it's not wrong, it just means that it's not linear at that point. It is also technically homogeneous because when we write it in the standard form, this side is 0, although we don't need that information for the method we're going to use to solve it. It's true. Yeah, and this happens to be separable, which I don't know if that's technically a classification. Sounds like it should be a classification, but it's really a method. It just means that we can use the method. And what that, well, I guess it is a classification. So it's a classification, and it means that you can separate out the variables with p and the variables with t. And to do that, we divide both sides by dt. So we'll have dp equals k p dt. Then we divide both sides by kp, or just by p. We'll just divide by p. I like that better. You could do it either way. So we have 1 over p dp equals k dt. Then, now once you have it in this form, you have dp with only p's and no other variables. You have dt with only t's and no other variables. Here there's no t, and k here is a constant. You can take the integral of both sides, which we already did. It'll be exactly the same as over here. You'll take the integral of this side. You'll only need one constant because you would technically have two, but you could later combine them into one. The integral of 1 over p is a natural log of the absolute value of p, normally plus c, but once again, it's not needed here. Then you're going to raise e to that thing, and you're going to end up with p. And you don't need to write this here, but just as a reminder, p is a function of time. It's always there whether it's written or not. So p equals, and then on this side, the integral of k with respect to t is k times t. Then we raise this side, you need to keep the plus c. So k times t plus c. We're going to raise e to the whole thing. I'll kind of scribble this over here. E to the k times t plus c. Then this is the same as e to the k times t times e to the c, due to the properties of exponents. And then this can be rewritten as some new constant, which we'll just rewrite c because we're lazy, but technically it is a different constant, c e to the kt. And that's actually what we're going to write here, c e to the kt. And you'll notice this is the same as what we had in the first equation. Derivative of y equals x times y. We got y equals ce to the 1/2 x squared. This is almost the same. And here's, if these were the same, the c's line up with each other, the e's line up, the k lines up with the 1/2, but instead of the independent variable squared, meaning x squared, we have the independent variable to the first power, just t. So that's the only difference between these two. There's other methods that you could solve this, which I think, well, hold on, actually I need to take a step back. So what we're actually looking to find, I had a good, yeah, I don't have, so there's other methods for solving this. So this is solving it as in solving it this far. We can actually solve it farther because we can calculate c. Because here we have our initial conditions. We have a start time. We have a certain time that matches up with a certain size. After 15 minutes, we have this population. So that means we can plug these conditions in to calculate for c, which we'll do in a second. But there's other methods that you learn to solve these. And so this was I feel like there should be a name for the method. Separation, I guess. It's just separating the variables and taking the integral. I don't think there's a nice name for it. If there is, I don't know what it is. So there's that method. There's also a method that you learn called the integrating factor. I haven't reviewed this in a while, and I'm honestly not. I think there's some equations that you can solve with the integrating factor, but not with the method of separating variables. I think that's why they do it. To be honest, it was a small, already almost out of my brain. It was in the beginning of the class. But basically, so to use that method, let's get back to our equation. We had dp over dt equals k times p. And here, we need to write it in standard form, which I actually already did once up here. So we have dp, hopefully I don't mess this up. I haven't reviewed this because it's not going to be on our final, but dp minus k times p equals 0. Then what you need to know here is the standard form for the linear equation is that I'll use y. So y, I think it's y prime plus p of x times y equals q of x. Yeah, that looks familiar. So in this case, p of x equals negative k. And once again, if I wanted to, I could change that to a positive k because it's just a dummy constant that's going to be filled in later. So if I keep it negative here, when I solve for k, I will get one answer. If I were to change it to positive when I solve for k, I'll still end up with the same true equation. I don't know how to say it better than that. So q of x in this case equals 0. So the integrating factor method was kind of complicated to explain in the first place, and it's based off of the product rule from integration. But just to memorize like the process, or just to show you the process without explaining like why it works. Basically, you're going to come up with this integrating factor, which you could call it whatever. They have been calling it mu of x, and I noticed that some other people do. And mu of x equals e to the integral, I'm running out of space, of px dx. And I'm using x's and I'm using y's, but technically I need to be using capital P's and T's. So that's going to matter in a second. So this is what you're going to use for your integrating factor for this particular problem. And I have enough space to write it one more time. So mu of x in this case will equal e to the integral of p of x here is negative k. And it's not actually p of x, it should be p of t. So it's going to be dt, which equals, I think it'll fit, so e to the negative kt. Yeah, just barely fit. So e to the negative kt. And once again, there would be a plus c here normally, but because this is in the middle of the process of this equation, and we have, I guess I'll say undetermined constants at various places throughout the equation, well, we can just leave the one undetermined constant at the end. That's the way I described it isn't necessarily always true. I don't think that was the best explanation, but for this, basically for our purposes for this problem, we can do that. So now then what we're going to do is this mu of x, which we figure to be e to the negative kt, we're going to multiply both sides of our equation, which was the derivative of the population with respect to time minus k times population equals 0. So we'll get, hopefully this still works when it's equal to 0. Most of our example problems it was not equal to 0, so it should still work. So we'll get, so dp over dt minus kp, sorry, this side then should be multiplied by e to the negative kt. And then this side, which is 0 times e to the negative kt equals 0, which is why I'm not sure if this is actually going to work out. So then for this side, if I have this right, it should be that because it's intentionally chosen that you use this formula to come up with your integrating factor, so that the end result should just be p, whatever your independent variable is, times the integrating factor kt equals 0. For some reason I'm not so sure that's right. And because of the product rule, something doesn't look right though. I think I actually still need that there because that k would be that c, I think. I did something wrong. Maybe I actually do need to multiply it through. I think I needed this kp on the other side. Oh, think for a second. If it were e to the negative kt dp dt equals ap times e negative kt, and then this were to become, not going to work either because then those are going to cancel and it doesn't make any sense. Oh, well, I wasted 5 minutes of the video and I don't think I'm going to re-record it. What I did wrong. Man. Sure that's right. But maybe you can't do it when this side equals 0, because when I multiply by e to the negative kt, I'm going to get 0. And this should be e to the negative kt. Well, actually, no, you can't divide by 0. I don't think this side is supposed to be 0. Maybe it can't work. If in our example problems, I don't think that side was ever 0. Well, booey. Anyway, getting back to the original problem here. Because I'm not going to remake the whole video. So P of t equals CE to the KT. We have this as our general solution for our population modeling, what we started on before I took that 5-minute tangent. And now we can fill in C because we have these starting conditions. Not actually starting conditions, but these conditions that will allow us to find our specific equation that we want, as opposed to our just a family of equations. So P of t, which here t is 15 minutes. So, and P of t represents the population at time t. So at time 15 minutes, our population is 10,000. 10,000 equals C e to the, wait, we also don't know k. Our initial size is 500. I think C is supposed to be 500. Yes, C is supposed to be 500. So how to say why? I think you can say, let me go back a step. All right. One more. Okay, so P of t at time 0, which doesn't have to be given, we know that. Well, actually, okay, so we were given that initial size is 0. So at time 0, sorry, that's not time. I don't want time on that size. At time 0, we have 500. So P at time 0, the population is going to be 500. There we go. Equals C, which we still don't know, times E to the K, which we still don't know, times T, which is 0, because this is time 0. This is 0 minutes. And this is going to be 0 times K is 0. E to the 0 is 1. So what we're left with is C equals 500. There we go. Now, so we know that P of t equals 500 e to the kt. We still don't know k. Now we can plug in the other conditions and find k. So we have 10,000 equals 500 e to the k times 15. Right beside it, 15. So now we can solve this for k. We would divide by 500, which, if I don't make a mistake here in my head, this should be 20. Hopefully I did that right. Yeah, 20 e 15k to get oops, equals, sorry about that. Now we can take the natural log of both sides, which I do not know the natural log of 20 in my head, so I'm going to leave it that way. Natural log of 20 equals, and when we take natural log of e to the 15k, you can bring 15k out to the front and just say 15k times natural log of e. The natural log of e equals 1, so it's 15k times 1, or just 15k. And then now k equals natural log of 20 divided by 15. This, now let's see what number we get. I'll use a calculator, and we're going to have P of t, population with respect to time, I guess that's the right way to say that, equals 500 e to the k, which is natural log of 20 divided by 15. I really like Desmo's website. Free plug for them. Hope they don't mind I'm using this, my video. Natural log of 15. Oh, it's a very small number. I was expecting a big number. I'm not very familiar with logarithms, so we're going to round that to 0.2, so it's really close to 0.2. And I don't feel like writing a whole bunch of decimal points, so 0.2 times t. So this then would be our specific solution to the differential equation that we set up from the problem, which was dp over dt equals kp. And we can actually graph this solution, but we can also graph the family of solutions that's represented by p of t equals ce to the kt. So normally you would technically graph that with a field, like a slope field graph, and you would also have to have this, no, sorry, this one. You would have to have the k found first, which now that we've found k, we could plug k back in, and we could actually plot the vector field for k. So k is, let's say 0.2. It rounds to 0.2. So dp over dt equals 0.2 times p. If you had a calculator that could graph slope fields, or not, maybe not a calculator, actually probably it would be a computer program that could graph slope fields, then you could plug dp over dt equals 0.2p in and see the slope field that would show you a visual representation of all possible solutions to this differential equation, or you can graph it by hand, which is very time consuming with the method that I showed earlier. You can also kind of cheat and get a rough idea from a regular graphing calculator. I was thinking I did it with the actual differential equation part before, but I'm not so sure. It's been like 2 months ago that I did that, so maybe I didn't do it there. I might have done it here, and right now to me it makes more sense to do it here, so this is how I'm going to do it. So we'll take this, and the 500 was given in the problem. The k was found by the other conditions, but what we can do is we can graph with both, what did we call this earlier? We called this C. We can call this C, we can call this K, and then vary those in different ways and see what possible different solution graphs could come up from this family of solutions. And so it's kind of like a secondary way without a fancier calculator or a very time-consuming slope field to see get a rough idea of what possible graphs are solutions to your differential equation. So we're going to go, but for Desmos, this is going to be considered y, and t is going to be considered x, because those are the variables that Desmos recognizes. And if you can change it, I don't know. So it's easier just to do it this way. So we're going to have c e to the kt. So c e to the kt. Oh, you can't see my I'd like it if equation showed up. I didn't realize it wasn't showing up before. Sorry, I got too many screens. Alright, we'll leave that there, and then we'll move this one. I'm not so concerned with the negative. Alright, c e to the kt, except I can't use t, I have to use x because it confuses it. So we want c and k to both be sliders. Now, if c equals 500, which is what we have in our specific problem, and k equals the information above it, so we'll say 0.199715. Then our graph, which maybe this wasn't the best. Not what I wanted. Okay, well, you saw the function there. I'm gonna have to zoom out. Oh, you know what? I think I made a mistake because it shouldn't be all negative. So I made a mistake somewhere in my calculations because that shouldn't be all negative. The 500 should be correct. I wonder if that's actually... So it's growth and not decay, so let's go back to our problem. Oh, it changed my size of my... Alright, there we go. So, PFT equals 500. Something's not right. That's minus 500, isn't it? So I came up with PFT, which we found that C was 500, e to the kt. Well, unless the numbers that I made up just aren't realistic enough, because I did just make up the numbers. So at 500, yeah, that's why it's negative, because we're not positive until we reach 500. So I don't know if there's a way to zoom out. I'm kind of stuck with I only have so many inputs for my laptop, so I can't use my regular mouse. When I full screen, you guys can't see the numbers. So let's go. Yeah, okay. So we're positive at 500. This was just a really bad example. Those numbers. So at 500, we are at 0. So 0 is the time, and 500 is the population. And if we continue to move up here in population, because I made the numbers so that the graph doesn't show up very nicely, you'll see we hit 2,150 as early as approximately 7 seconds. Yeah, so maybe those weren't the best numbers to choose for an example. And then at 9.6 seconds, we hit 3,400. Anyway, so you get the idea. It shows the population. And if it were a little easier with me not having to try to balance two screens and use my mouse pad instead of my mouse. Oh wait, let me slide this back to normal. So now what I was trying to say though about changing, you can sort of get an idea for how the differential equation behaves without plotting the full slope field, because you can slide these sliders around. So let's make our starting condition like really low. That's actually still high. All right, well, let me just make our starting condition 2. So now you can see, I don't know if I can zoom in. If I had my mouse, I'm pretty sure I could just zoom in, but really hard to slide all this stuff around with the way I have everything set up. There. So that looks like a more comfortable to look at graph. Okay. Now, so at 2, which you still can't see on here, but 2 should be at times 0, we have 2 bacteria, and we still have the same growth rate. But you see, if we change the growth rate, so changing the C will just change where our 0 position is. Changing the growth rate will actually, the K value will actually change the way the shape of the graph. And so if you were to draw the different lines across the slope field with the different types of starting conditions, this is kind of the different line possibilities you would get. So actually that one's not all that interesting. It just wiggles back and forth a little. Oh, and eventually if you hit the right exact number, it flattens out, which is probably 0. Yeah, it would be 0. So for other graphs, it's a little more interesting to do that. But anyway. Okay, so let's see. So that was that. Now, if I take and move on to the next thing. How long is this video getting? Really just wanted to make this all in the one video. All right, so the next thing, so we did population. Integrating factor I sort of did, but I botched it. I'm going to try one more time with a problem that looks more like what we would have seen in class, and see if I don't botch it this way. So dy over dx plus 12y equals 4 at the with starting conditions y of 0 equals 0. Now, the integrating factor, once again, so this is already written in the form that I had described earlier. So we have the form would be derivative of y plus p of x times y equals q of x. And here, and then also you need to know mu of x, or the integrating factor. I've seen some YouTubers abbreviate it this way, IF for integrating factor, whatever you want to call it. I'm calling it mu of x, but it just means integrating factor, is equal to e, the integral of your function p. Now, for our specific problem, we have e of x equals 12. There's actually no x in there, it's just the number 12. U of x equals 4. Once again, there's no x value in there, so it would be like x equals 4, or y equals 4, I guess would be. Anyway, so there's no x in there. Mu of x is going to equal e to the integral of 12 dx. The integral of 12 is just 12x, so this is going to be e to 12x. Normally that would be a plus c, but it's not needed here. Then you multiply both sides by mu of x, so you get e 12x times, I'm going to write dy dx as d prime, as y prime, plus 12y equals 4e 12x. And now this should turn into, so there's like some kind of magic that happens here, and it's based off of the product rule, and pretty sure it just becomes 12e. I think maybe it's y. I think if you keep the 12, I think you don't. I think it's just y e to the 12x. I think you just keep y equals 4e 12x. That doesn't look right because we're just going to divide that out and get y equals 4. That's the problem. I don't remember how to do this method. Alright, I'm not going to talk about this method. It's not, unfortunately, apologize for wasting time twice now. I haven't done it since the beginning of the class and I don't remember exactly how to do it. So, moving on to the next thing. So then one of the next things that would be talked about that is of interest is the idea of a leaking tank. This comes again from the practical example type problems. There's also mixing problems, which we will do one of those later, hopefully, eventually. This is getting really long now. But if we have a leaking cylindrical tank, and a good setup for the problem, which I pretty much kept the word problem the same and just changed the numbers, but water leaks from a vertical cylindrical tank. So let's try to draw this. We have this tank. Okay. Believe it or not, I actually draw pretty decent. It's very hard to draw on a tablet. So this is our tank, and it's got a hole in it. We'll just put it on the bottom, and there's water coming out of it, making a little puddle on the ground. And a certain amount of water in it. So we have this tank. Water leaks from a vertical cylindrical tank through a small hole in its base. This is the hole, at a rate proportional to, there's the proportional to thing again. So we're going to say the rate of change of the volume of the water with respect to time equals, and there's this proportionality constant again because it says is proportional to. The water leaks from a vertical cylindrical tank through a small hole in its base at a rate proportional to the square root of the volume of water remaining. So the square root of the volume. So the rate of change of the volume with respect to time equals proportionality constant times the square root of the volume, once again, with respect to time. I guess, I don't know, the volume, I think you have to say with respect to time. That sounds like the most Englishy way to say that. So let's say the tank initially contains 300 liters of water and 50 liters leak out during the first day. So day 1, we have 50 liters that leak out. So when will the tank be half empty in days? So let me write that. In red. I'll write that down here. When will the tank be half empty? So that's what we want to find. So we have our equation set up, our differential equation. So you should be able to solve this by integrating factor, but for some reason I keep screwing that method up, so I'm obviously not going to use that method. This should be, this is separable, so we can solve this by separating the terms, the variables. Yeah, I think that might be it. So we're going to go with the method, this separation method, because I seem to be having the most success with that one. So multiply both sides by dt. We're going to get dv equals k times square root of v is the same as v to the 1/2. And then we have our dt. Now we're going to divide by v to the 1/2. I'm going to keep the k on this side. You can move it to the other side, whatever you prefer. 1 over v to the 1/2 dv equals k dt. Now you can take the integral of both sides since you have the terms by themselves. I'll do this easy side first. So the k can technically come to the outside and you just have integral of dt, which is t plus c. So we're going to have k times t plus c. And you'll notice I did a little verbal switcheroo there because the same thing, how this is a constant and this is a constant, what you can have this k times both t plus c or the k times the t plus the c, and it ends up in the end being the same thing because the constant is just like a dummy placeholder for now. And when you change it in the proper way by multiplying it by another constant that's in the problem or something like that, when you work out in the end to solve the c, that will automatically come into play to get you to the correct value of c that you need for however you set up your problem at the moment you tried to solve for c. So then this, we're going to use substitution. Yes, I think so. Oh, let me think for a second. So you think we have to use substitution. No, we don't. Silly me. This is just a negative integral of v the negative 1/2 dv. There. So now then, this is going to be, oh, my brain's fried. So we're gonna add 1 to the exponent, so v the 1/2, then divide by that new exponent, which dividing by half is the same as multiplying by 2. We would add a plus c, but we have it on the other side, kt plus c. We need to get the v by itself, so we're going to divide by 2. V to the 1/2 equals 2kt plus 2c, but once again that 2 doesn't need to be multiplied by that c. I'm not sure if that applies to the k or not. I'm just going to multiply it by the k. I think it does, because the k has a t with it is y, but at any rate it doesn't need multiplied by the k. So then we're going to square both sides. Yes. So v equals, hopefully this is correct, I'm getting very tired at this point, kt, 2kt plus c squared. For some reason that didn't seem like the solution I think I should have gotten. Negative 1/2 v to the 1/2 v to the 1/2 divided by it, that's negative. Everything seems okay. So this is our formula for our volume. So in other words, rewriting that, we have the volume at a point in time equals 2 times k times time, which time here is in days, plus c squared. And the initial conditions that we have are, we start with 300 liters, so that means it should have been very initial starting. Yes, so that's, and if it starts with 300 liters, that means at time 0. So v of 0 equals 2, well actually this whole thing goes to 0, because it's 2 times k times 0 plus c squared. So we have 0 equals c squared, 0 equals c. So now, rewriting our equation with our value for c, we have v of t equals 2kt squared, oops, whole thing squared. And now we can solve for k, because we have at day 1, we have 50 liters. So 50 is our volume. Wait, I didn't do that right. This wasn't supposed to be 0. This was not supposed to be 0. So v of 0 is equal to 300 liters. So now we have 300 squared. So this part was correct. So we have not 300 squared. We have c squared equals 300. So c equals the square root of 300. So c equals the square root of 10 times 10 times 3. So we're going to have 10 square root of 3. C equals 10 square root of 3. Now we can write in our c value. So v of t, I'm just going to plug in this day 1 value at the same time because I'm going to end up running out of space. So v of 1 day equals 2 times k times 1, because t is 1 here, plus 10 square root of 3 squared equals 50 liters. And then we can solve that. So 50 square root of both sides, so square root of 50, that's 5 times 5 times 2, so 5 square root of 2. 5 square root of 2 equals 2k plus 10 square root of 3. Subtract square root of 3, 5 square root of 2 minus 10 square root of 3 over top of 2 equals k. And now you just rewrite this whole ugly thing. I guess I'll figure out those. Well, I'll just rewrite it real quick. I'll rewrite it down here. So, no, I am going to figure out decimal equivalents because it's going to make it a lot easier. So we're going to do some rounding. So we want 5 square root of 2 square root of 2, it was minus 10 square root of 3, all of this divided by 2. Yep, and that is equal to, we'll call it negative 5. I'm going to try to keep the numbers really nice and simple. So k is negative 5, approximately. So v of t equals 2. So negative 5 times 2 would be negative 10. Negative 10 t. C then is 10 times square root of 3. So 10 square root of 3, which is, we'll call that 17. I keep the numbers kind of simple. Plus 17 squared. So now the question, the actual question was, when will the tank be half empty? So we want to get volume is 1/2 of the initial volume. So the initial volume was 30 liters. So we want to know when will it be 150 liters. So we're going to set this up. I'm really running out of room, so I'll set it up over here. So we have 150 as our new volume equals negative 10t plus 17 squared. Square root of both sides, we're going to get square root of 150 equals negative 10t plus 17. I'm going to subtract 17 and divide by negative 10. So negative 17 plus square root of 150 divided by 10 equals t in days, which, if we plug that into a calculator just for curiosity's sake, we're going to have 17 plus square root of 150 divided by, I think it was 10, negative 10. Oops, negative 10. So 0.47, which is really close to 1/2. We'll call it 0.5. So the answer is in half a day, as long as I didn't make any calculation mistakes. So there. So that was another example of using a differential equation. I'm going to try to go through my whole list here. We're probably a little over halfway done. So okay, the next thing to talk about is a method of constant coefficients and undetermined coefficients, and this would normally be broken up into several sections, each building up to the harder part, but I'm just going to just start where I start at. So let's take this problem. second derivative of y minus 2y prime plus 1 equals cosine of 3t. Now, a couple things going back to those labels. I probably should have just wrote those labels over here. I thought I was going to come back to this, but I haven't yet, so I probably won't, honestly. As far as what type of an equation is this, it is second order. And that's true because of this second derivative. The highest derivative we have is a second derivative. It is linear as opposed to nonlinear, and you can see that because I have it written in standard form, and none of the dependent variables, which the dependent variable here is y, none of the dependent variables or their derivatives are raised to a power other than 1, multiplied by another dependent variable or another derivative. Like, so there's no y prime times y, for example. Also, there is no like sine of y, sine of a derivative of y, those kinds of things. There's probably some, to give a more full list, there would be more things to say, but that's like the rough idea. So second order linear, it is non-homogeneous because this right-hand side, when it's in standard form, does not equal 0. So the first part of what we went over was like the first part of the class, and that was basically those were first order. I think all of them were first order differential equations. Well, except for the first one where I had acceleration. Pretty much all of the rest of them were first order differential equations. And this here is an example of a second order differential equation. The methods that you can use to solve them are generally different. So the one example from earlier actually was a little tricky because it was sort of a second order, but actually I was using it as a first order because acceleration is the second order of position, second order derivative of position, but it is the first order derivative of velocity, and we were considering it as a first order derivative because the main non-derivative function we had was velocity, not position. So let's see. So how to solve this? Basically, the reason that, so when you're learning these, they go over many different types of these first before they build up to this one, and this is kind of the capstone of the different methods. The different methods, the different. It's not the first one you would learn. There's simpler ones you would learn in other types, but this is a good like complicated one to give full coverage of the basic types of examples. And the main difference, one of the differences is this is non-homogeneous. So you would start with homogeneous where the right side equals 0, but you actually have to solve this the exact same process. When you solve a non-homogeneous, you just do extra to it when the right side is not 0. So you solve it first as if the right side were 0, and then solve it additionally with the right side not being 0. The other thing about this is the method of undetermined coefficients. And as we go along, I may forget to mention it, but it may become evident why that's the case. And it's actually really complicated, so this is just going to be an example. Getting tired. Coefficients. Okay. So see what else. Then the other thing is for the first part of this, when we solve it as if it were homogeneous, there's 3 different types. We're going to be finding this value r, and you have where r is real and unique. The values of r are real and unique. Then you have where r is complex. And then you have where r is repeated. Just for like, for this there would be 2 values for r, so where r is 1 value repeated twice. I actually am not sure which type I set up here, but we're only going to go over this one, not the other types. So the first step to solving these is you pretend this is going to take the entire page. Let me get rid of this. I'm never going to use that again. So we're first going to pretend it was, that's as far as I can go. So y double prime minus 2y prime plus 1 equals 0. So we're going to solve this first. In solving this, we basically changed the r primes to r to whatever power that is. So this becomes r squared minus 2r plus 1. Actually, this should have had a y. Does this need to have a y? There should have been a y there. Pretty sure that needs to be a y. One y. Otherwise, it's really going to mess up my. Going to be even harder to solve. So let's make that a y. Because I think if this is just a 1, we need to move it to this side over here with a non-y's and non-derivative of y's. So let's make that a y. R squared minus 2r plus, so now this is a 1, sorry. This one's a y. This one's a 1. Equals 0. I picked one that factors, so this is r minus 1, and that's it. So this is a repeated. R minus 1 squared equals 0. That's positive 1, and the 2 together, negative 2. Yeah, so here we have r equals 1, and it is a repeated root. Repeated. Maybe I don't know if root's the right word, repeated. I guess r probably stands for root. I'm not sure. Anyway, it's repeated. So now we're going to have to use, I should have picked one where it wasn't repeated because that's the more basic form. But basically, the final form that this is going to take is going to be some form y of, sorry, not the whole thing actually, that's not true. The final form that this homogeneous version is going to take is the form y equals c1 e to the rt plus the t plus c2, oh, sorry, keep forgetting there's no vision over there. All right, so y of t equals c1 e the rt plus c2 e to the rt, where this is r1 and this is r2. And the problem is, if I use this r equals 1 for both values, then both of these terms will be e to the 1 times t. So it'll be some constant e to the t, some constant e to the t. And based on some really like fancy mathematics, that can't be the case. You can't have repeated terms. So the solution then here for this type of problem is to tack on the lowest necessary t variable. So if there's already a t in here, like if it was t e to the rt for whatever reason, then you would tack on t squared e to the rt. If there was already a t squared, you tack on t cubed. If there is no t, you just tack on t. So that's what we're going to do here. So then our solution, which in this case it's y characteristic, y sub c, that's what they call it. The final full solution is going to be the y of t equals y characteristic plus y particular. Right now we're finding y characteristic. If the original problem up here did not include cosine of 3t on the right hand side and just included a 0, then finding the y characteristic is actually the full, that's it, that's all you find and you're done. But this is a two-step problem right here. So y characteristic equals c1 e r1 t plus t c2 e to the r2 t, and I wrote R1 and R2 even though I shouldn't have. They're the same. It's a 1, and actually I should have just wrote the 1. So let me rewrite it. yc equals c1 e to the t plus, I'm going to switch the order, c2 t e to t. So that's the characteristic solution. And I think I didn't give initial conditions, so we won't be able to solve for C1 and C2. The final answer will have C1 and C2 in it. Now for the next part, I don't know if there's a better way to say this. The way it was explained to me, though, I don't like the terminology, but it was explained that you basically make a guess for what y should be, and then you plug that in with the y, the derivative of it, and the second derivative, and you solve, and you see if your guess was right, and if it was, then you kind of have your answer. That's a weird way to explain it to me though, because like whoever first did it was probably making a guess, but there's actually basically a chart that you can use. So you'd have like 10 or so different things you would look up or memorize. Depending on what this right-hand thing is what you're going to want to plug in for y. So when the right-hand thing is cosine of something, you're going to use cosine of, let's say beta. Well, we'll just say 3. Whatever the number is here stays. So cosine of 3t, you're going to use a cosine of 3t plus b sine of 3t. And that's what we're going to use to plug in for y. Yes. And then we take, so this is in a sense y particular. You would often, well, and this is also why it's called undetermined coefficients. These are technically undetermined coefficients, C1 and C2, but those are always there. These are new types of undetermined coefficients that are not always there and will be able to be determined without initial conditions so that we can get our solution to only have C1 and C2. So we have these. Now we need to have the first derivative to go here and the second derivative to go here. So the derivative of the particular equals the derivative of a cosine of 3t is going to be negative 3a sine 3t, and then the derivative of the other side will get us to plus 3b cosine 3t. Don't know why this is in here. Then we have the second derivative particular equals sine and cosine. We don't flip signs, so it'll still be negative. We multiply this out, it's 3, so we get 9 a cosine 3t plus, oops, actually this time we do flip the sign because cosine to sine, you flip the sign, negative 9b cosine of 3t. So that's what we have. And if I can even fit this across here, let me rewrite this down here to save it. Y characteristic equals C1 e to the t plus C2 t e to the t. And then I'm going to erase some of that because I'm going to need that space. And we don't need this either. Still does it? Okay. I'll switch colors. Alright, so now we're gonna, oh, I needed the original problem. Well, I have the original problem written right here. So our original problem was y double prime minus 2 y prime plus y equals cosine of 3t. Now, we're filling all of our things that we just calculated in. So y double prime is going to be this. So we're going to have, or can I go? Oh, I messed up that down there. Y of c equals c1 e to the t plus c2 t e to the t. Off the screen. So we have -9 a cosine of 3t minus 9b cosine 3t minus, I'm just going to distribute this now. So minus 2 is going to get distributed to all of this. So we'll have plus 6 plus 6 a sine of 3t minus 6 b cosine of 3t plus a cosine 3t plus b sine of 3t. Now, and then equals cosine of 3t. So on the right-hand side, on the left-hand side, we have a bunch of terms that are in terms of cosine of 3t or sine of 3t. On the right-hand side, we have a cosine of 3t. So we're going to want to think of this as 1 cosine of 3t, and so we're going to add to it 0 sine of 3t, because 0 times sine of 3t is 0. So we didn't change the equation, but we're going to make use of that, and you can write a 1 here. So on the left-hand side, we're going to try to get collect all of the cosine terms together, then pull out the cosine of 3t, then also collect all the sine terms together and pull out the sine of 3t, and then we're going to end up with whatever was next to the cosine terms, set that equal to 1, whatever was next to the sine terms, set that equal to 0, and then solve it all for a and b. Then once we have a and b solved, we can plug them back into the full y function for y that by tacking on the y characteristic equation. So I want my cosines first. So here's a cosine, a b, here's a cosine with a b, here's a cosine with an a. So we're going to have, I'm also going to do the pulling out at the same time. So we have a, and then this is -9b, -6b, plus -15b, a minus 15b, and then that's all times cosine of 3t. Be right, a, yep. Yeah, that should be right. And then as far as these signs go, so we'll have plus, for sines, we have 1a, 2a, and 1b. So -9a, positive 6a gives us a -3a. And then we have plus b times sine of 3t equals 1 cosine of 3t plus 0 sine of 3t. So now a minus 15b equals 1, and -3a plus b equals 0. And let's solve for b equals 3a. I just added the 3a. Oops, there. I moved this 3a over here. Now we can plug this b value into the first one. So we have a. This is going to be negative 15 times 3, which is negative 45. Negative 45. The a, I switched it to a b. 1. We can factor out the a, so a times 1 minus 45 equals 1. And we're going to get a. I'm going to divide by this, so 1 divided by, and I'm also going to do the subtraction and move the negative sign to the top because it looks better. Negative 1 over 44. So that's what we got for a. Now we know that b equals 3a. So b is going to equal negative 3 over 44, assuming I haven't made any calculation errors in all of this. So now we can go back to our characteristic equation, our particular equation, which was right here, and we're going to plug in a, and we're going to plug in b, and then we're also going to combine it with our characteristic equation. So the final solution for this is y of t equals c1 e to the t plus c2 t e to the t. A was negative, so minus 1 over 44 cosine of 3t. B is also negative, minus 3 over 44 sine of 3t. And this is as full as we can get for our solution. This is the general solution to the differential equation that we had set up at the beginning. The C1 and C2 will change depending on your starting conditions, which I did not give. So that is the method of undetermined coefficients, and honestly, that's most of what is covered for solving second order equations in a direct format. Then the next thing that I'm going to talk about is, well, I was going to do an example, but this is getting really long, so I'll just briefly say after this then is a discussion about some applications of equations like this one right here. And the application is a spring system. And this one, is this the same? Yeah, that was this late in the course. So basically if you have a spring, so this is a spring, pretend this is like the tabletop or something that it's sitting on, and you have some mass sitting on top of that spring. You can use this type of equation to model that. You can also use this type of equation to model current moving through a circuit, but we spent a lot more time dealing with the mass and spring system. So basically, that would be m times the second derivative of the position, which I'm using x. You could use any variable, it doesn't matter, plus, they use c sometimes they use gamma. I liked it better when they use gamma. Gamma times the first derivative of the position plus k, the position, equals, and then this is either going to be 0 or f of x. If it's f of x, it's considered forced. If it's 0, it's considered not forced, or free, actually free. Free is what they call it. It's considered free. It means not forced, but anyway, that's the word they use. And basically, as you can see, this setup is exactly the same as this. So if we had some spring that had some force dealing with it, I guess acting on it, and that force could be represented by cosine of 3t, then that would be here. If we had then our position was multiplied by the constant, and I did know for the exam, now I can't remember anymore what this k represents. It represents something, I can't remember exactly. So, but anyway, here the k value would be 1. The gamma is the damping constant. So if there's no damping, the final result will be some kind of oscillation like forever. If there is damping, then the oscillation will eventually die down. That's oversimplified, but that's basically the idea. And you'll notice that this is derivative of position, so this is the same as velocity, or speed, velocity. And then this is the second derivative of position, so this is the same as acceleration, and this is gets multiplied by the mass. So if this up here had represented a spring, the modeling of a spring, then the mass would have been equal to 1. And I'm not going to actually go through another problem because that took forever to solve as it was, but the steps then would be exactly the same as far as working out the math goes. And then typically they memorize a lot of other vocabulary and some other random things such as damped, undamped, which I briefly mentioned that, and some other vocabulary that, to be honest, wasn't that interesting to me, so I can't really remember any of it anyway off the top of my head. So that's the basic idea there. Now, next thing. Get back to, let's try this dark blue. So, what's next? So then the last two things, which is actually what my test is going to be over tomorrow. I spent all that time talking about all this other stuff. The first one is called Laplace transform. Oh, there's a really crazy lag. So a Laplace transform, and basically the idea is solving differential equations directly, which is what I have spent the entire rest of the time talking about, is often very difficult and sometimes, quite frankly, not even possible, which is why they have Euler's method, which is a method of finding an approximation. So it can get you a decimal value that is very close to whatever the real value should be, but you can't get a like mathematically precise exact value. So, and Laplace transforms are a little bit weird to use. They feel very like theoretical and disconnected, even more so than the other stuff I've already mentioned. But what happens is you just do some magic math tricks and the algebra work out some algebra and it ends up much nicer. But it requires memorizing some charts, like depending on how many you have. We were actually given a list of 39 things to memorize, but then our professor kindly knocked it down to 10, which isn't so bad actually, because the 10 kind of follow some patterns, so it really only feels like 3 or 4. But basically, and actually I want to take an aside anyway, if anybody's still watching at this point, when you have, so in lower math in school, all the way up through algebra, there's not very much memorization. Ignoring geometry, but geometry just feels pretty disconnected from the rest of the math courses, whereas the rest of them kind of flow together and build off of one another for the most part, all the way up until you get pretty high into college math, I'd say. And up until trigonometry, there's not a lot of memorization, but once you get to trigonometry, you have to do all of these memorizations where you remember that something equals something else, and you have to know when to manipulate and to change between the one thing and the other thing. So I'm actually really bad at trig identities, but trig identities are a good example of that. Then when you hit calculus 1, derivatives are a good example of that. You have to memorize lots of derivatives, what the derivative of something is, you know. Then the same is true in the reverse for integrals. You have to remember that what the integral of sine is. You really can't calculate it. You pretty much just have to memorize it. And the same is true in differential equations for finding the y particular of a function. It's kind of intuitive. It's not like full memorization because it's kind of built off what's there, but there's a lot of memorizing to it. And then the other one is through right here, Laplace transforms. And so some examples are if you have, so if you have, basically what you're going to do is you have some function f of t, and you want to change it to a Laplace transform, you say, like it's written like this: Laplace transform of f of t equals something, right? I don't think I can. I feel like I should be able to write that better, but it equals something, right? Just do that. It equals something. So the basic idea, well, actually, I know what I should have wrote there. So the basic idea is that the Laplace transform of f of t equals the integral from 0 to infinity of e to the negative st times f of t dt. And basically whatever your f of t is, whatever function you have, and in this case they can be differential equations, you plug that in here, and then you just solve this integral, and whatever you get will have s's in it and no longer should have t's, because of after you compute the bounds from 0 to infinity, that's going to wipe out the t's. When it does that, you just have s's left as your variable, and you have some new function. And you can then use that to solve your differential equation. Just some short examples of what you would memorize. I'm not going to work out that. There's actually some guy on YouTube that has really good videos where he works all of these out. But some things that you would just memorize from a chart are the Laplace transform of 1 equals 1 over s. And you could compute that by solving this, which I don't even want to do that. So by solving this, and you would discover that when you computed by plugging this 1 for f of t into here, you would end up getting 1 of s as your final result. You can say that the Laplace transform of t to the n, which is actually much harder to compute using the original method, but you can do it. It equals n factorial over t to the n plus 1. I'll just write down two more. The Laplace of sine of beta t, which if beta is 1, then that's fine. You can pretty much ignore it. But if it's not, then you have to write it there. Beta t equals beta over s squared plus beta squared. And the other one that's really nice, Laplace of cosine beta t equals s over s squared plus beta squared. So basically what you would do to solve this is, well, I think I will show you. I think I have an example. Yeah, I have two examples, but maybe I'll just do one because this video is getting like crazy long. So if we have, let's say we have this y, derivative of y plus 12y equals 4. And I think I solved that. Did I solve that earlier? Yes, I did. And we want the initial conditions to be y of 0 equals 0. And we actually solved this earlier, and I didn't record the answer on my paper, and I already erased it from the screen. But we had solved this earlier using, I believe, the integrating factor method, which I may or may not have gotten correct because I was really having a hard time with that. But this is something I'm studying right now for my exam, so this method I will get it correct. But so we have, I do just have, yeah, the first derivative. So if we take this, another thing I should have wrote is the Laplace transform. There's actually a more generalized formula, but I don't even find it helpful. It's really complicated. So I think it's easier just to memorize the Laplace transform of the derivative of y equals s times big Y. Big Y stands for Laplace transform of y minus y at 0. And the Laplace transform Well, the Laplace transform of y, as I said, equals big Y, so I'm not going to write that down. And the Laplace transform of the second derivative of y equals s squared big Y minus s y0 minus the derivative of y at 0. So these you will use when solving these actual differential equation problems. So what we're going to do is plug in, we're going to take the Laplace of each term, and as said, and these follow the rules for integration, and I'm not even going to so if it seems like I'm doing weird magic, it's because they're following the rules for integration. So that's why we can do the Laplace of each thing, each term individually. So the Laplace of y prime, use parentheses, brackets, is s big Y minus y0 plus 12 times the Laplace of y, which is big Y, equals the Laplace of 4, which is best to think of this as 4 times the Laplace of 1, because you memorize the Laplace of 1. So it's going to be 4 times 1 over s. I think I'll actually write it that way, 4 times 1 over s. My s's and 5's are going to look the same. I apologize. There shouldn't be any 5's in this. These will all be s's. So then what we need to do is plug stuff in. S big Y. I'm going to move this 12y right next to it. Plus 12 big Y. And then minus y of 0, which we're given y of 0 equals 0. So minus 0. There's no need to write it down. Equals 4 times 1 over s. Now, we can factor out big Y, and then this equals, I'm actually going to put this back to 4 over s. I think it's going to be nicer. So 4 over s times, we're dividing both sides by s plus 12, 1 over s plus 12. So that is equal to 4 over s times s plus 12. And what do I want to do next? I didn't actually pay attention to how easy this was to solve or even solvable when I set it up. I think we're going to have to do partial fractions, which come up a lot in this method. If I distribute, I'll get 12s, and we don't want that. Yeah, we're going to have to do partial fractions. So this is equal to a over s plus b over s plus 12. This is from Calc 2, and I'm not going to try to explain even how to do it. Just see if you can follow along if you don't know it already. A plus b, then we multiply every term by the bottom of this, which is s times s plus 12, so we get 4 times, this is kind of an aside, this doesn't follow directly from this, 4 times s times s plus 12 equals a times s plus 12 plus bs, and then yeah, that's all we want. Sorry, no, those canceled. When I multiplied this on the top, we had it on the bottom, so this is, let me get rid of that. This is just supposed to be equal to 4. So now what we can do to solve this type of thing here is there's different methods. The one that I like and I think is the easiest is we're going to set s equal to some value that will cancel out either the a or the b so that we can solve. So for example, if s equals 0, this b term goes away. So let's do that. When s equals 0, we have a times 12 equals 4. Divide both sides by 12, we get a equals 1/3. Then we take s equals -12, and we're going to have, this time the a side goes to 0, so we're going to have -12b equals 4. 4 divided by -12 is going to be -1/3. So b equals -1/3. So now back to what we had above, we have y, big Y, meaning the Laplace transform of y, equals, a is 1/3, 1/3 over s, oops, erase it, s plus -1/3 over s plus 12. So then we're at a place now where we can do the inverse Laplace of both sides. So y is the Laplace of y. Big Y is the Laplace of little y. So when we do the inverse Laplace, we're going to end up with back to just y. So we have y of t, because y is y of t, it's the same thing, equals, if we move this 1/3 out in the front, we have 1 over s. And I said up here, the Laplace of 1 is 1 over s. So when we do the inverse Laplace of 1 over s, we get 1. So this is just going to be 1/3. And then we have minus 1/3. I'm pulling it off the top and out in front, times the inverse Laplace of 1 over s plus 12. And this is one that I didn't write down. If I have it memorized correctly, it should be the Laplace of e to the beta t equals 1 over s minus beta. So here beta would be -12 because it needs to be minus beta. So s minus -12. So we're going to have e to the -12t. E to the -12t, which should be the answer if I didn't make any calculation mistakes. And for a simple problem, I think this was easier to solve whatever the other method was I used to solve it. But if I start adding the second derivative in there and making these longer, it's a lot easier to do it often using the Laplace transform method. So there is an example of a Laplace transform in action, hopefully with no mistakes. And one more thing to cover is systems of equations, and this is actually probably my favorite part of it, the class. I've really enjoyed this, and I've also really struggled with it because linear algebra was not a prerequisite for this class, and I think that it should have been because it's referenced constantly in this section. So let's just go ahead and solve a problem. And once again, this is a very long problem. I'm liable to end up with the wrong answer, but the general process will be correct. I just might make some mistakes along the way. We're going to do systems of systems of differential equations, I guess. System of differential equations. And for this one, the ideas that would be covered here, there's definitions, there's some types to memorize, there's the idea of a unit step function, a Dirac something's like impulse, and some of those things to memorize. Then there's a reviewing of matrices in linear algebra, which are all pretty important to this, being able to solve these. But I'm just going to start with like one of the last examples that would be, oh, and then the other thing that's important is these examples may make use of these two things with kind of fancy names, but once you know what they're used, the process of using them, I don't think they're so hard. There may be more to them than what's used in these examples, but vectors. But I only know them from this example, from these systems of differential equations. And here they're really not so hard, actually. The rest of the stuff is actually the hard part. These are just like your goals during the process. So eigenvectors and eigenvalues. So What you want to do is you're given a system of equations that's usually set up with matrices, and you solve first for the eigenvalues, then you use those eigenvalues to figure out the eigenvectors, and from those eigenvectors then you can set up the resulting equation, meaning the solution. And the example that was given, and I really like this example, was a mixing problem, which were also used earlier with one vat mixing, but this is actually going to have two vats mixing, and they're pretty cool problems actually. So let's say you have these two vats. Oopsie. Yeah, we'll try this. I actually think I might get the final answer wrong because I attempted it. So we only set up these problems. We didn't actually solve them, and I attempted to solve it, and my professor pointed out something that I had wrong, and I understood his comment, so I may be able to do it correctly the second time, but I can't guarantee that. So, but the setup I know how to do really well. So pretend there's these two cylinders, they're vats, they're holding some liquid that has some concentration of some mineral in it, and we'll go with salt as the example, which is what's often given. There's a pipe that's connected between these two here. There's a pipe that's connected between these two here. This pipe has a drain. The bottom, there is a pipe connected. I like it better if we put it right here. And the same thing, there's a pipe connected right here. Draw this little circle. And these are filled with fluid above both pipes. I would have put the pipes lower, but it was harder to draw them. So just pretend their fluid's always above the pipes, because I'm not calculating for anything other than that. So we have some water and solution flowing this way, water and solution flowing this way, water and solution flowing this way, only one way, and water and solution that flows this way. Some of it goes out, and some of it flows into the other tank. So these are tank 1, tank 2, and I will also call them A and B because it's going to make the variables nicer. And then we need some numbers. So before I do that, let's set up the basic idea for the formula, and that is we're going to say that Q of A equals quantity, or I didn't put the A, quantity or concentration of salt, and Q of A would be the quantity in A, Q of B would be the quantity in B. Then the derivative of the quantity with respect to time is going to be the rate of change of the concentration over time. And again, it'll be with respect to A or with respect to B. And the next thing is the general formula for these is, just erase that down here. So the rate of change of a quantity with respect to time equals the rate in times the quantity, we'll say concentration in minus the rate out times the concentration out. And that's general actually for a lot of the differential equations that you set up. You have rate in minus rate out, and in this case the rate in is the rate in times the quantity in, because the rate in, what will be given, will be the rate of the fluid, and what you really want is the rate of the quantity. So when I set up these numbers, it'll make more sense. So I'm going to make up these numbers and I'm going to try to make them kind of nice. So let's say, and I also think that for this to work, for our example that we did, the amount stayed constant, and I'm going to keep it that way because I don't feel like trying to make the video long enough to work through whether you have to or not. I'm not sure if you do. So let's say we have like, and we'll do the units, liters, minute, and grams, I guess. Yeah, so let's say we have 4 liters per minute of a concentration that has 3 grams per liter of salt. That's what's flowing in here. What's flowing in here? Let's have 2 liters per minute and 5 grams per liter. And then what's flowing across here? We will have, so okay, so I think these need to add up. So we have 4 in, let's have 6 out, let's make them add up to 10. So 6 liters per minute from A to B. Then we have, right now we have 2 in, wait. Okay, so we have 4 in here, 6 out. Oh, no, I know, I want this up top to equal this down here. So we have, so that the height of the liquid is staying the same. Let's do that. So we have 2 in here plus 4 in here, so that's 6. So let's go with 6 liters per minute out of this. And then we have 4 in here, 6 out, which means we need 2 in. But then this one, is this one changing? So we have 2 in, plus we would have 8 out, plus 6 in. Yeah, so let's do 2 liters per minute here. So that's 2 liters per minute that makes it from B to A, and 6 liters per minute that makes it from B out to the floor. This is like a puddle on the floor. So now, when you set this problem up, we have, this is going to be a system of equations. So we have the first one will be in reference to tank A. So the rate of change of the quantity of A with respect to time equals the rate in, which is first going to be 4 liters per minute, times 3 grams per liter. So that's going in. Then we also have this going in right here, which is 2 liters per minute. So it's still going in, so it's going to be positive, plus 2 liters per minute times this one. Then the quantity coming in is based on the concentration in B. So it's going to be times the quantity in B, which is going to be in grams, concentration, quantity. Yeah, I think concentration is correct. The concentration in B divided by, which I forgot some of my initial conditions. So let's say that tank A holds, this one looks bigger, let's make it 100 liters. This one looks smaller, let's make it 50 liters. And the other initial condition that we would use would be, let's say that A starts with 0 grams initially, and that B also starts with 0 grams, because that's going to make the math easier at the end if I want to actually solve the whole thing. So initially these are pure water. So the quantity in B divided by 50 liters, so that's going in. Now we need to subtract what's going out. So minus, And the outbound, there's only one lane. It's right here. It is 6 liters per minute. And it is going to be multiplied by the quantity that is in A, which the quantity of A changes, so you have to use the function Q sub A, and that's going to give you grams, and what you actually want is quantity in A, the grams, per 100 liters. That's the concentration. I was mixing up those two words earlier. So, and to double check, the final solution, the rate of change of the quantity of A with respect to time should be in grams per minute. So it's a change in grams per minute. And so here, liters per minute times grams per liter, liters cancel, you have grams per minute. Here, liters per minute times grams per liter, liters cancel, you have grams per minute, and the same thing over here. And then we do the same thing for B, so the rate of change of the quantity in B respect to time equals so going in, we have this up here, 2 liters per minute times 5 grams per liter plus this inbound right here, 6 liters per minute times the quantity coming in from A, which changes, so it's going to be once again Q of A divided by 100 grams, it's liters. So this is B going into B, this is going into B, coming out of B. We could set this up as two different ones, or we can set it up the same. So we have B is going out to here and B is going out to here, but from the perspective of B, it's just one outbound lane, and the flow rate is 2 liters per minute here and 6 liters per minute here. So the total flow rate out of B at this point is 8 liters per minute. So this is minus 8 liters per minute times the quantity in B, which once again is changes. So quantity in B in grams over volume of B, which is 50 liters, because this is concentration. Q of B is the quantity of B. Q of B divided by 50 is the concentration in B. So that is how you set up the problem. To actually solve the problem, which I will attempt to do and hope that I get correct this time, is going to be, I'm going to drop all of the units now, so let me rewrite this. This is dq, and actually I'm going to just use the quantity of A, the derivative of the quantity of A with respect to time equals 12 plus 1 over 25 QB, and then minus 3 over 50 QA. My numbers were not so nice. And then I just wrote that off the screen a little bit. QB, change in B is going to be equal to 10 plus 3 over 50 QA minus 4 over 25 QB. Now, so no, I wanted these to be equal to 0 actually. The amount flowing in at the top I wanted to be equal to 0, not the initial here. But let's see if I can try to solve this anyway. So what this is going to boil down to is, if we write it in the more standard form, this is going to get really ugly. We're going to have quantity in A plus Q plus 3 over 50 QA minus 1 over 25 QB equals 12. You know what? Actually, I don't think that's right either. I still don't know how to set these problems up. So anyway, you could use matrices to solve this, but unfortunately we didn't actually solve these, and the matrices we set up don't set up to turn into that. Because what we want is so big Q quantity, meaning it's a vector or a matrix, equals, and putting the terms in order, I'll do the QA's first. So I'm going to multiply this times QA and times QB. So no, actually I need to have those on the left and the right. So I'm gonna put QA first. Negative 3 over 50. And then the other QA is 3 over 50. QB is, on the top is 1 over 25. On the bottom is negative 4 over 25. And then A was first, so it should be on the top. QA, QB, and then we have at the end plus 12 over 10. And I would solve this, but I don't actually know what to do with the 12 over 10. So the reason is, unfortunately, I don't think I'm going to be able to figure it out either. Well, I know what I did during, so I can show how to solve this if the 12 and the 10 were not here. Which the 12 and the 10 come from these numbers up here. So let me do the exact same thing, but pretend that we had 0 flowing in. So if we had 0 flowing in the top, 0 liters per minute, so this isn't even here, there's nothing flowing in the top. And we had 0 flowing in the top up here. Then the equation would be the same except without this 12 and this 10. That's where those came from. So if the equation had looked like this, without the 12 and the 10, then I can show how to solve that. So I'll just do that. I don't know what to do with the 12 and the 10 exactly. So in this case, then we would take and we find the eigenvectors and eigenvalues. So it's still going to be flow, so there'll still be salt flowing. And actually, technically, the initial condition. So the initial conditions don't come in until the end, which means I didn't want to make these 0. When I set this up, I actually wanted to make these up here 0. So let's say that these do have starting salt. So let's say this is 405 grams, or let's say 400 grams. And this one looks smaller. Let's say that it has less salt. Let's say it's 200 grams. Now it might be actually more interesting. Let's make them the same. They're both 400 grams, but they have different volumes and different flow rates. So basically the end result here is that eventually there's no new concentration of salt flowing in. It's all going out. So eventually it will all end up on the floor. And actually, so let's say that there is water flowing in the top. Let's keep the 4 liters per minute. But when you set up the equation over here, it's going to be 4 times 0. 4 times 0, so it'll still go away, or 2 times 0. Let's also say there's 2 liters per minute flowing in the top. So the amount of water is not going down in either tank, it's staying constant, but eventually the salt is being washed out of the system. This I do know how to set up correctly, so we'll work this problem. So we have, first thing we want to do to solve this, which this is, these matrices represent this up here without these, because I put the 12 and the 10 at 0. So this is the same as this. It's just written in matrix form. And first thing we want to do is this fancy word called find the determinant of A minus lambda I, and then set that equal to 0. And all this is looks complicated, and the details are kind of deep, but the actual practice is very simple. And the lambda I, the I is just converting the lambda into a matrix. It's the identity matrix. You don't really need to know that. The A represents this here with the numbers, the 4 numbers. So we're just taking A and we're subtracting lambdas from the top left and the bottom right. And then we're setting that thing. We're taking that thing and finding the determinant, which means to multiply the diagonally this way and subtract whatever you get multiplying diagonally this way. And we do that. We find this first though, so it's going to be negative 3 over 50 minus lambda times negative 4 over 2, 25, negative 4 over 25, minus lambda, and so on. So, and I really wish these were better numbers, but negative 3 over 50 minus lambda times negative 4 over 25 minus lambda. And then we're going to subtract these two multiply together, which this is, I'm going to need a calculator for just about all this. So let me get this set up. Okay, so 3 I know, what's 25 times 50? It's going to be 1,250. So minus 3 minus 3 over 1,200, what? 1,250 equals 0. So we combine all these terms here, we get lambda squared. This is going to become positive, this is going to become positive, and we'll add them together. So 3 divided by 50. I'm just going to convert all these to decimals and use approximations to make this a little easier. So 3, yeah, I'm going to do that. 3 divided by 50. 3 divided by 50 is 0.06 times 4 divided by 25, 4, no, plus 4 divided by 25 is 0.22. So plus 0.22. Then now we 4 over 25 times 3 over 50 minus that. So times minus 3 over 1250. 3 divided by 1250. 0.0072. So and which one was bigger? Okay, it should be correct. So it's positive plus 0.0072 equals 0. And obviously I don't know how to factor that, so I'm going to have to use the quadratic formula. So or to do it this way, negative b plus square root of b squared minus 4ac divided by a assign variables. Why it doesn't do them in order, but a is 1, b is 0.22, and c was 0.0072. 0.0072. Oops, what happened there? 72. So we have they're negative, which is nice. So I don't remember. Okay, so that's not the section that I am as familiar with. So hopefully I can do that without messing it up. So there's just as before with the equations, there'll be slightly different steps depending on whether at this point you get positive numbers, negative numbers, positive numbers with two distinct solutions, negative numbers with two distinct solutions, or a repeated solution. There'll be a slightly different process for each possibility. So we have, and the whole point of this is to find lambda, and when we find lambda, that tells us our eigenvalues. So lambda 1 equals negative 0.04, 0.04, and lambda 2 equals negative 0.18, negative 0.18, and these are the eigen values. So that's step 1. And since our eigenvalues are distinct, but they are negative, we have to do that, follow that line of reasoning. So the next thing we need to do is we need to calculate the eigenvectors. And so if we have lambda 1 equals negative 0.04, the eigenvector for this, we're going to do the same kind of thing, but it's going to be a little different. We have a minus lambda I times k as a vector equals 0. And if you're doing repeated values, you want to do like k1 and k2 because there'll be two separate vectors, but for this there's just one. So you don't need to use them again later, that is. So we're gonna, this a minus lambda I is the same as before, but now we know lambda is negative 0.04. So we're gonna start with negative 3 divided by 50 minus negative 0.04. So that's negative 3 divided by 50 plus 0.04. Negative 3 divided by 50 plus 0.04 is going to be negative 0.02. So we're setting up a matrix. Try to continue to work down. I'm hoping to fit this all on one page, but it might not make it. So negative 0.02. The other two don't change. So 3 divided by 50 and 1 divided by 25 don't change, but I want to do them in decimal form. So 3 divided by 50. 3 divided by 50 is 0.06. 0.06, and then we have 1 divided by 25. Divided by 25 is 0.04. Oops. 0.04. And then in the bottom right corner, we have negative 4 over 25 minus negative 0.04. So negative 4 over 25 plus 0.04. Negative 4 over 25, 0.04. So it should be negative 0.12. Negative 0.12. And we are multiplying that times the vector k, which will fill it in with k1, k2, and it should be the same size in height as our other vector. And we're setting it equal to 0, which actually is 0 as a vector. So it's 0, 0. We're going to multiply, and technically you would multiply both, but due to the nature of these things, it should be the same. The top and the bottom should be multiples of each other, and in this case it's pretty clear to see that if you multiply the first row by -3, you're going to get the second row, and you can see that just by looking at it. So we actually only need to multiply the top row times k1, k2 and set it equal to 0. So what we have then is -0.02 k1, was supposed to say k2, plus 0.04 k2 equals 0. Then we just kind of solve this. So I'm going to add k1 and then divide. So we're going to get 0.04 k2 divided by 0.02 equals k1, which equals 0.04 divided by 0.2. Should be 2, but 0.04 divided by 0.2 is 2. So what we have then is k1 equals 2. So we set up our eigenvector, and we have k1 on the bottom, because that's where I had it up here. We say k1 equals 2. When k1 equals, well, so I should actually do it the other round. Say k2 equals 1. You could do it, it's the same difference, but it would have been a little easier to say k2 equals, all right, hold on a second. Yeah, it's easier if you just set it up and then don't actually do that solving part. So when I divided these, really if I think of it as 2 times k2 equals k1. And then what that's telling me, because this is not a solution, this is a proportion. So you can put in lots and lots of different numbers for k1 and k2 and get the statement to be true. Basically, you want to pick, for the eigenvectors, you want to pick a small value, something that's easy to work with, but not 0 except under certain circumstances. I would generally avoid 0 because most of the time k1 and k2 could both be 0, and it's just not going to be useful to do that. So pretty much it's usually in your best interest to put a 1 somewhere. And in this case, it's easy to see that if k2 is 1, then 1 times 2 is 2, and we're left with 2 equals k1. So this is the eigenvector for lambda equals -0.04. Now we need to do the same process to find the other eigenvector. And I'm going to try to squeeze it down here because we still need lots of other space. So lambda 2 equals -0.18, -0.18, and our matrix. And this time I'm going to use a shortcut. I'm only going to do the top half because we only need the top half. So we have the original one, -3/50 minus -0.18. So -3/50 plus 0.18, -3/50 plus 0.18 is going to be 0.12. Numbers weren't really that bad. So in the top left we would have 0.12, and in the top right that doesn't change, so we would have 0.04. And I don't actually need the bottom row because I'm not going to use it anyway. But it's technically there. I'm just not going to solve it for it. k1, k2 equals 0 as a vector. So we have 0.12 k1 plus 0.04 k2 equals 0. We can subtract whichever one we want. I like to make k1 1, so I'm going to try to do that. So that means I'm going to subtract this and then divide. So I have 0.12 divided by 0.04, which should be 3. And this is times K1 equals K2, except this was supposed to be negative because I moved it over and then divided. So this should be negative 3. So when K1 equals 1, K2 equals negative 3, so long as I didn't mess that up, this is your other eigenvector. So now what you need to do, you know what? This would have been if we had real solutions, but we have imaginary solutions. And my video is already really long. So, no, we didn't have imaginary solutions. Yeah. Yeah, we had two distinct real solutions. They're just negative. Yeah, okay. So we had two up here when we solved for lambda, when we solved for our eigenvalues. We had two real solutions. They're just negative. So that doesn't matter. I made some comments earlier about that mattering. That doesn't matter. It would have mattered if they had been complex numbers, or if they had been a repeated solution. So there's lambda only equaled one thing that was repeated twice. But since we have two unique solutions, then we're actually following like the easier way to do it. So now I need to take, and it's the final solution is going to be y of t equals d1 e to the lambda t, so negative 0.04, negative 0.04 t times whatever eigenvector was associated with the eigenvalue. So 2, 1 plus the other one. So plus C2. And you'll notice this is very similar in form to the characteristic equation. It just happens to have these vectors in there. And technically, this should not have been just y of t like that. It should have been, what even variable was I using? Q. This should be q of t, and I already used capital Q, but this is q as in vector q, not just function q, which normally you would distinguish by capital and lowercase, but I already used capital, so I can make it bold, but I can't. So this is a vector, this is a matrix, q of t. C2e to the negative 1.8, negative 0.18 times the other, the eigenvector associated with that eigenvalue, so 1 over negative 3. Sorry, it's not divided by the vector 1, negative 3. And there we go. There is the solution, but we can actually solve for C1 and C2 because I gave some values up here, 400. So the quantity, which is in grams, the initial quantity, the quantity at time 0 is 400. That's what this says. So we can solve, and then we can actually graph. So what we have here is C1 times e to the negative 0.04. Here, I'll do this, q of 0 equals C1 times e to the negative 0.04 times 0, which is going to be the 0, which is going to be 1. So we can ignore that. So it's going to be C1 times 2, 1, plus, this was supposed to have a t here, sorry. So C2 e to the negative 0.18 t. So this goes to 0, and then this goes to 1. So it's going to be C2, 1 over negative 3, C2, 1 over negative 3 equals these values. And technically, when I laid these out, I believe this was QA. It has to match this format here. QA on top, QAB on the bottom. But here, they happen to be the same, so it doesn't matter. So equals 400 over 400. And now we solve this. So the way that this works is this C1 goes with the top and the bottom. This C2 goes with the top and the bottom, but otherwise the top and the bottom are separate. So this is going to be 2 C1 plus C2 equals 400 And then C1 minus 3C2 equals 400. And then we just solve. Let's do the bottom one, I guess. So C1 equals 400 plus 3C2. So 2 times 400 is 800. And what was this? Plus 3C2. So 6C2 plus 6C2. I'm trying to save writing because I'm almost out of space on my page. Plus C2 equals 400. Subtract 800, we'll get negative 400. Add these two together, we'll get 7. So we'll get C2 equals, to be negative 400 divided by 7. C2 equals negative 400 divided by 7, which equals, we'll do decimal format because that's what I've been doing. 400 divided by 7. We'll call it negative 57. We'll just call it negative 57. So negative 57 equals C2. Now for C1, use this one. So 400 plus 3 times C2. And I'm not going to round it yet. I'll actually use the number since I have it on the other page. So we're going to multiply it by 3, we're going to multiply it by negative 3, and then add 400. So times negative 3 plus 400. I think that's what I said. So we have, where was I at? So it should be about, 57 times 3, but this is negative, that's negative, so it's going to be positive. So it'll be about 150, 400 minus 150, that should be positive. It is positive, no. This was negative 57? No, I needed to take the negative twice because then when I bring it to the other side, so it should be 400 minus that. 3. $400 minus that. That sounds better. So we'll call that 229. So C1 equals 229. Now we actually have our system of equations. And it's based off of this. So in matrix form, Q of T equals C1, which is 229 e the negative 0.04 t times the vector 2, 1, and then it would be plus C1, C2, but C2 is negative, so minus 57 e the negative 0.18 t times the vector 1 for negative 3. And that is the final solution. You could also write it as two separate solutions. So if you follow the top half, it's going to be the quantity in A. So Q of A equals 229 times 2 e to the negative 0.04t minus 57 times 1 e to the negative 0.18t. And then on the bottom half, we have, which I guess I'm actually going to want to write that because that's how I have to enter it in to graph it. So we're going to have to clear some space because I have no room whatsoever. Delete. This is almost done. Switch colors even. All right. So the way I wrote it below is a solution, but it is also appropriate to write it as Q of A, respect to time, So some function of the quantity changing over time, the quantity of salt equals 229 times 2. I might as well just do that. Probably 458. 9 times 2. Yes. 458 e to the negative 0.04 e. No, that works. I'm rewriting it anyway. I didn't realize I wrote it behind my camera. So I took care of that too. So negative 57 times 1 is negative 57e to the negative 0.18t. Then on the bottom, the quantity, the function that represents the quantity in b with respect to time equals 229. This time is multiplied by 1, so we have 229e to the negative 0.04t. Negative 57 times negative 3, which also, I don't know, say like 172, I think. Negative 57 times negative 3. No, 171. So, plus 171 e to the negative 0.18t. And that's technically it. However, the really fun part then is to see what actually happens in our tanks as this solution flushes through. And so as I changed the problem so that I knew how to solve it based on the initial setup, we have clear water flushing in the top. We have salt in the tanks to start with. The salt flushes back and forth between the tanks at a certain rate, and also flushes out from tank B down to the floor at a certain rate. And so we'll be able to see when we graph this that rate of the salt in each tank decaying over time. And if I did it correctly, it should eventually go to 0, but I might have made a mistake somewhere because there was a lot of calculating. So let's see what happens. And we don't need any of this stuff. So we have 458e. Actually, we'll just write the e's first. E to the negative 0.04. Oops. E to the negative 0.04 times x. We gotta use x and y. And then we have e to the negative 0.18x plus e to the negative 0.18x. Yes. No, like those are too close. Now for our constants, we have 458 and 229, 58, 229, and we have negative 57 and positive 171. Negative 57, positive 171. So this should represent the graphs of both of those over time. And they do both go to 0, so there's a good chance that I was correct. You can see, let's see, where's, I don't know why the zoom feature is all the way over there. Yeah, that's what I should have did at the start of the video. There, now you can see the whole thing. So as I zoom in, you can see kind of what happens. So anything to the left of 0 doesn't mean anything. We can see that, and these are whatever I called them. I think I called them minutes. The time represents minutes, so the x-axis represents minutes. We have, it looks like they have the same, is that where they have the same quantity of salt, I believe? or it's really close. I think usually when you click on it, it should show you the dots. So when you click on a dot on this in Desmos, it locks in if there's some kind of a crossing point nearby. It'll lock in. So 0, 400 is where one or both of these are crossing the axis. I could zoom in, but I'm not going to. Which actually makes sense. They should both be crossing the axis at 400 because I set the starting condition so that each one starts with 400 grams of salt. And we can see that the A should be the purple one because I put A on the top. Let me move this over a little and you can see everything there. So A here starts at 400. It's the purple line, and it goes down a little bit slower. So like if we were to take some time right here, which is approximately 5 minutes, 5 minutes, tank B has 250 grams, but tank A still has about 340 grams. So you can see that tank B decays much faster than tank A, which to be honest, I guess you wouldn't need a graph to tell you that. It kind of makes sense because they both start with the same amount, but tank A throws some of it to the floor. Tank B throws some to the floor. Oops. Whereas tank A only throws some to tank B. Did I get those right? 458 was on the top. A is on the top. A is purple. Yes, no, it does make sense, and what I just said was backwards. B is red. So no, B is red. 229 is B. B is red. B is losing salt faster. So this is 50 minutes. B has around, well, actually that's 30 minutes. Wait a second. No, 50 minutes, 30 grams of salt. So here, 50 minutes, we have about 60 grams of salt. So tank A has a lot more salt than tank B because, yes, okay, it does make sense because I removed, wait, so tank A has salt that gets pumped into tank B. Yeah, okay, it makes sense because the amount of salt going into tank B is going to be whatever is in A flowing in at 6 liters per minute. The amount of salt in A is going to be whatever is in B flowing in at only 2 liters per minute. So we have much less salt coming in. And also you could have looked at it by the amount of clear water going in, the amount of clean, oh, and I cut that part of the graph off. Whatever number I had up here represented pure water going in. So we have 4 liters per minute. I think it was a 2. I think we had 2 liters per minute going in here, whereas we had 4 liters per minute going in here. So that A would be getting cleaned faster. No, B is getting cleaned faster. Ugh. So I actually don't remember what number that was. B is getting cleaned faster. Well, anyway, it's possible that I made a mistake somewhere, but I'm not quite sure how that. All this salt going into B. Yeah, because we have more salt coming in. I think that's the way to think about it. Because we have more salt coming into B from A through this 6 liters per minute. The thing that needs to be assumed, and I forgot to mention this at the start of setting up these problems for these math classes, you're making a very false assumption for the purpose of making the math work out, because it is to practice math, and if you try to set this up realistically, it's just much, much, much harder. So it's assumed that the very moment that any gram of salt enters, that it immediately, instantaneously disperses equally throughout the solution. That's required. So as soon as any salt enters tank A, it immediately disperses evenly throughout all of tank A instantaneously. And then the same for B. When something enters B, it immediately spreads evenly the concentration of salt throughout the entire tank. So anyway, uh, whatever quantity is in A is assumed to be traveling with a faster flow rate into B. So that should mean more salt, because if the concentration is the same in the both, which, oh, actually, and that's something I forgot to take in, the concentrations won't be the same because this is a smaller volume. Actually, that's probably why I was thinking wrong. Probably the reason that B is clearing out faster. Yeah, anyway. So there's that, and there's pretty much probably a good place to end my video on talking about differential equations in however long this has been, 3 hours.